Here we are, Math 2265, and we are for the lecture of March 15. I have a little Irish music playing. I hope that's okay. Maybe it's a little loud. We'll turn it down if we need to. But we are in the middle of 4.3, I think one of the most important sections of the book, if not the most important one, followed by a couple of miscellaneous sections that, well, shall I say, pale in comparison. But I will want to cover them. Yes, it's good to have a few more distributions under your belt, but the normal distribution dominates the procedure here. So I just wanted to make sure that you see the priorities involved. So we are going to look at this part of the Z alpha notation for critical values. Now, the Z alpha notation is really looking for something to the right of Z. So as I try to circle it there, right of Z alpha, we're looking for the non-cumulative region. So we're so used to the cumulative region, it seems like this notation, well, it's just extra notation. It's not my favorite, but it is useful, I suppose. We're looking at especially a right tail or a right portion. And 1 minus alpha is actually more important because that's the cumulative situation, the distribution function. So anyway, Z.10 captures the upper 10%, Z.01 captures the upper 1%. So it can be useful for top 10, top 5%, that sort of thing. But Z alpha, in terms of the cumulative percentile works cumulatively from the left, as you know. For example, this 0.10 would be the 90th percentile, 1 minus 0.10, and this would be the 99th percentile, 1 minus 0.01. So that means Z alpha is the 100 times 1 minus alpha, the percent of the standard normal distribution. So anyway, negative Z alpha looks an awful lot like Z alpha. All you do is change the sign. So if you go to the percentile, this is a handy table for which we see several popular values. The 90th percentile means that you've got 10% to go, 0.1, and on the table or on your calculator you'll find to 2 decimal places it's 1.28. 95th percentile, we actually talked about this. They actually split the difference here, a rare situation, 1.645, and a few others that aren't perhaps as popular. Actually, this one is quite popular because it stands for the 95th percent confidence interval, but that's another story for another day. 1.96, probably the most important Z value of all for reasons that we'll see in another chapter. And then the 99th percentile is 2.33, and this 99.5 percentile, the top 0.5%, is up to Z equals 2.58, 2.575 in some books. And then some others that are rarely used, with the Z values being exponential, they're just inching along. They seem to almost peter out at about 3.5, although it is technically possible to get Z values larger than that. Okay, so the 95th percentile is Z of 0.05. This Z alpha notation is facing to the right. The percentiles are facing to the left, just like a cumulative function would do. And so they show some symmetries here. This is a little tough to read. Maybe I can expand it. Maybe I can't. Sometimes it lets me, sometimes it doesn't. Oh, that's a lot. Okay, so we have the Z.05, 95th percentile, 1.645, but then the mirror image of that is at negative 1.645, which is the opposite of Z of 0.05. So that would be the same thing as the 5 percentile, 5th percentile. Either way, the shaded area is 0.5. And we'll have more to say about that one later on. But this one has some popular values. So let's move on and try something else. They call it the non-standard normal distributions. That's not the word I would choose, but it works, I guess. So we will standardize X into Z. The most important formula in all of statistics, one that you should memorize, of course having your formula sheet just in case you forgot to memorize it, is Z equals the data value X minus the mean mu divided by the standard deviation. And it's kind of ironic that you guys are right at the same level as my Math 1101 class. It only sees statistics for 3 or 4 weeks throughout the semester. And you guys are just perfectly lined up. That was not done on purpose. And they certainly see it on a lot lower level than you guys do. But it's still the same material. They just get the overview fast version. You guys get, well, sort of a fast version that's rather deep compared to theirs. So they're going through the stuff that they've already shifted the z over. And I wouldn't drag into A and the B and all that. I would have just calculated the z's in advance based on the x value and the mu and the sigma. Would have just found them already. And they like the phi notation, which is fine. It just says that you could find the cumulative values from the table or from the calculator. But if you're using the calculator, you may as well just type the whole thing in, such as normal CDF, min, max, mu, and sigma, sometimes 0 and 1 if it's already standardized to a z. So that's for the TI. And others, you'll just have to look up their websites and see what they say. Or, of course, you could always do it by hand, and a table is allowed on the test. Okay, so we're going to go from the lower limit A to the upper limit B. And Z has been adjusted already. And they have the integral notation, which also works from negative infinity up to what works out to be a solution for x. If you reorganize this formula, then you get the comparable version of x equals mu plus sigma z. Very easy to multiply by sigma, add mu to each side. That happens to be the limits, the upper limit, as we see here. Okay, equality of non-standard and standard curves. Oh, wow, I just saw some lightning. That's amazing. Didn't get any rain at all yesterday after 9/10 of an inch, and sorry about the diversion, but the lightning was rather dramatic as I record on Friday afternoon, late. Okay, so we have, here's the standard normal with a mean of 0 and standard deviation, say, of 1, and some sort of typical value here. In a more generalized normal curve, you'd have just a general mean, whatever it may be. It could even be negative. And the sigma will have to be positive, and they like to talk about sigma squared in this book. I just call it mu and sigma usually. 1 squared is the same as 1, so it doesn't matter very much. And they've converted it here also to a z-score. So these are the z-scores. These are the raw data. So whatever you choose to work with. The z-scores are nice to know, but with the calculator, they may not be absolutely necessary. But your book is traditional and rather deep book. Well, let's look at this example. I'll spend most of my time on examples today. The time that it takes a driver to react to the brake lights on a decelerating vehicle is critical in helping to avoid rear-end collisions. I got caught in a sandwich once where the guy pushed me into the other car, and of course the car was eventually totaled, although it took them a while for them to decide that. It suggests that reaction time for an in-traffic response to a brake signal from standard brake lights can be modeled with a normal distribution having a mean value of 1.25 seconds and a standard deviation of 0.46 seconds. What's the probability the reaction time is between 1 second and 1 3/4 seconds? And x can denote the reaction time, and one can convert over to z and find out what the z values are. So they put extra notation in, which nothing wrong with that. The bottom line is that z will be from less than the mean at about negative 0.54 up to a little more than 1 standard deviation on the high side of the mean. And of course, the higher reaction time, the longer reaction time rather, is not a good thing. It's not a good thing at all. But we're looking for the window of opportunity on a calculator. You can either type in the raw data, such as min of 1, max of 1.75, along with the standard deviations, the mean and standard deviation, so 1.25 and 0.46, or you could convert it, although that's basically unnecessary. You could get a little round-off error involved in this, and go from minus 0.54 to 1.09 with the mu of 0 and the standard deviation of 1. So you could type those 4 numbers in instead and get pretty much the same answer. Well, what about this last one? 2 seconds is a critically long reaction time that will almost for sure get you in trouble. That actual reaction time, luckily, is only about 5%. So as they go through and find the z value, which works out to be 1.63, pretty far away from the mean, and we get to 0.56. I'm going to take a look at the table. I don't expect you to be using the tables much, but let's see about phi of 1.63. What would that be based on the table? So positive 1.63. Notice we have our units and tenths on the left column, the hundredths on the other columns, and so I'll go to positive 1.63, and 0, 1, 2, 3, it looks like 0.9484. But we're going to need 1 minus that number. 1 minus 0.9484 is 0.0516, and I believe that's what they got over here. Yes, 0.0516. So table can be useful. I would say, I don't expect anybody would depend on it, but it's nice to know about. You just never know. Plus, it's always good to have a different perspective. That's the way I look at it, even if you don't use it that often. Standardizing amounts to nothing more than calculating a distance for the mean and re-expressing the distance as some number of standard deviations is all we're doing in terms of z. So if mu is 100 and sigma is 15, commonly used in IQ tests, by the way, x equals 130 would correspond to using the formula x minus mu, finding a difference of 30 for this IQ score, which they have it labeled as an IQ score, would be 30 points above average. Divide by 15 for the standard deviations, and this person would be at a 2.00, 2 standard deviations above or to the right of the mean value. And 85 would give us 85 minus 100 over 15 is a negative 1. So this would be 1 standard deviation below the mean z of negative 1. Okay, here's another example. The breakdown voltage of a randomly chosen diode of a particular type is known to be normal. And what's the probability that a diode's breakdown voltage is within 1 standard deviation of the mean value? So whenever they say within, they're talking about plus and minus that number. They could even use absolute value. Z, absolute value, is less than or equal to 1, is the same thing, of course, as between negative 1 and 1. And as we know, with a continuous distribution, we don't care if we use the less than sign or less than or equal. It just doesn't matter. Your book does, however, like to use the less than or equal sign. Okay, I've seen several books that just use less than, but that does not matter because this is a continuous distribution. You know the area of a line is 0. Anyway, they go between 1 and minus 1, and they find, as you look up the values in the table, I guess I can take a quick look at the table. How about 1.00? That's a value of 0.8413 cumulatively. And negative 1 is 0.1587. You subtract those out, you're at about 68%. And here's the picture. Cumulative value comes in from the left. In this case, would be chopping off that left tail and finding around 68% in the center. So at least you have a visualization that a calculator might not, well, might be able to give you. It depends. And I've got a cat jumping up on me now, so I'll try to get around her. Anyway, we have that, and we also have within 2 standard deviations, and one could check the table or your calculator and get around 95, almost 95.5%. Within 3 standard deviations is practically all of it. There's some thunder. Wow, some real weather here. 99.74%. That's quite a lot. That's all but 26 people out of 10,000, or cases if they're not people. So this is called the empirical rule, and this is also one I just taught. They didn't call it empirical, but I called it that. So rounded to just the nearest decimal place or so, 68% are within 1. The big one is the 95er. That's the one we see the most. 2 standard deviations, and that z value of 1.96 will play a role in this in making it exactly 95%, not just approximately 95%. And then just go to a next decimal. Why did they do that? If they'd gone to the nearest percent, they would have said 100%. That doesn't sound quite right. So they did bend it back just a touch, and that's within 3 standard deviations of the mean, which is virtually everything. So it's indeed unusual to find something that's much farther than 2 from mu, and the tables stop at around 3.5 and negative 3.5 because there just isn't much left out there. I guess I could take another quick look at the table. Yeah, the smallest value on the table is 0.0002 minus 3.49. The highest number is at 0.9998. So that's also just 1 minus 0.0002. So they could go a little further, but it goes so slowly at the end. All these numbers are repeating themselves to 4 decimal places at the end. So they just sort of lose momentum at that point, and I don't blame them. Even when people did use tables all the time. Okay, let's see here. What's next? We have percentiles of an arbitrary normal distribution. Now this is an important one because so many times they want to go for percentiles. So the 100th percentile of a normal distribution, this is cumulative again, for a normal distribution, mean of mu, standard deviation sigma, is related to the percentile of the standard normal distribution. So we're going to just take x equals mu plus z sigma. This could be called your x value. Of course, there's mu. This is the standard normal. This is z. And that is sigma. I guess I have a little trouble annotating right now, so I'm not going to try to do that right at the moment. So another way of saying this is that z is the desired percentile for the standard normal. It's the same one in terms of z standard deviations from u. Okay, anyway, let's take a look at an example. And the authors of Assessment of Lifetime of Railway Axle. So we have an initial crack length and number of loading cycles to propose a normal distribution with mean value of 5.496 millimeters, standard deviation 0.067 millimeters for x equaling final crack depth. So what value of this would be exceeded by only 0.5% of all cracks under these circumstances? So if that's the high side, only 0.5%, wouldn't that mean that's the 99.5 percentile? 99.5 percentile. In other words, the cumulative total, x is less than some value c, that would then equal as close as you can get to 0.9950 if you're using the table. So you just approximate. I see no need to interpolate, except for that one special case where you actually got to 1.645. But I wouldn't do that. I would just use your calculator if possible. Anyway, I use the formula that we saw before. I wish I could type it in, but I am verbalizing x plus, or actually mu plus x, u plus z theta. I'm sorry, mu plus z theta. I've got confused with another value. This is the x value. They're calling it c right now because c is playing the role of x for a moment. Well, anyway, starting with the mean, because that's like the center spot, you start with that and then you go up or down depending on where you're headed. So around 5.5. And then you look up in the table, or maybe you find it from a calculator, 2.58, which corresponds to a certain confidence interval we'll talk about later. And 0.067 is the standard deviation. So that means that we add a small amount, and we're going almost to the end of the line here, speaking of railway axles. And we can only move it over to about 5.7, almost. And they're taking it to 3 decimals here. So here's the distribution of the final crack depth. Here's the mean. Here we have 99.5% behind us and only 0.5% ahead of us. And it didn't move the needle that much. Just the way it goes. The standard deviation is rather small, so it takes a lot to move it even a little bit. More lightning. Wow, this is very dramatic. Okay, let's move on and see about our next topic and see what we can do about it. The normal distribution in discrete populations, especially the binomial distribution. This is something that's more or less done to show you patterns and cases in math that we can use. And it turned out it used to be very, very vital, but it still plays a role, so we're not going to ignore it. But I'm not going to emphasize it either. So what we just covered was some of the major parts of the class. Now we're going to slide downhill just a little bit, but we can relate perhaps the top 2 distributions together, and the normal distribution and the binomial distribution, which that's what they're headed for. They're just preparing you for just general topics. And you can use it as an approximation just to show you that these things can be done. Occasionally when you have very large numbers, you may find your calculator cannot calculate them for you. I've even found numbers that go into the thousands that even software has lots of trouble calculating. So at some point, these approximations can still be needed if you have large amounts of data. Believe it or not, the software can't quite keep up. Unless, of course, you get some sort of high-powered computer that I am not privy to, and then perhaps you don't have much need for it. If you work with small data sets, you probably wouldn't have much need for this, but let's take a look anyway, even if it's almost like teaching the square root method. Just, I'm kidding here. Yes, there is a square root algorithm. Does anybody really use it? Not really. I looked upon it as a history of math type of topic, and so this is almost that way unless you work with large data sets. So here we have IQ, as we mentioned before. U is 100, sigma 15 for most IQ tests. So what if we looked for a probability that a selected individual, randomly selected, has an IQ of at least 125, which is not too shabby. So we'd like to find the probability of X being greater than or equal to 25. But of course, you are what you make of what you are. I'll never forget a guy that used to come in a math lab. I work in a couple of math labs, and he was certainly challenged. He had difficulty speaking, and at first glance you would think, what is he doing in the math lab? Is he taking arithmetic? Oh no, he was taking first-year calculus, and he made it into second-year calculus before he finally dropped. But he was in there, it seemed like every minute of the day. He was there as much as 10 hours a day. This guy was perseverant plus. So anyway, sorry to ramble on, but IQ is one thing. make the most of what you have, whatever it may be. So anyway, 125, not too bad, I guess. So we standardized this, put it into the Z form, and we would do that. Not too hard to do. 25 is the difference between 125 and 100 over 15. That's going to be 1 2/3, 1.67 for the Z. Well, anyway, let's take a look at the histogram. The rectangles of the histogram are centered at integers. These are really trying to form like Riemann sums. So there's another little comparison we can make for you. The 125 really starts at 124.5 and goes to 125.5. Yeah, that's what happens. We're trying to approximate a curve with a bunch of blocks, the histogram bars. So but yet we want to go above 125. So instead of worrying about the 125.5, we'll just worry about the 124.5 and go on up to wherever. Call it infinity. If anybody had an infinity IQ. Well, anyway, when we standardize this, it isn't 1.67. It works out to be 1.63. The math is easy, of course. And now we find that going on up using, I think we actually did this one. We actually looked at this value already, ironically. And we find it's the upper 5%, 5.16%. So that's how many people we would expect, or what proportion of the people we would expect to get. Whereas if we had not standardized it, just used 125 blindly, we would have trimmed off a part of the rectangle. You see the left part of this rectangle would have been not included. That's not good for Riemann sums, and it's not good for approximations in statistics either. So they do insist that you do go back and get that other part. The numbers that would round into 125 as a discrete number, like 124.5 would round into a 125. And so that is counted as far as, oh wow, maybe you heard that. That thunder is really something. Anyway, it's an interesting time right now. The storm isn't over. So we see that we didn't gain that much. We did gain a little bit, and it is more accurate. And one could then actually look up the answer or figure out the answer from the actual formula, and maybe they'll do some of that as well. This is called a continuity correction, and it's useful in calculating various things that can be done, especially when you have large data sets and you're not able to actually do this by hand. I've been fond in the past of finding numbers that most people cannot get on their calculator, just so you'd have to use approximation. So I'm going to teach it. Let's see if we can use it, perhaps. I'm not going to say 100%. It just seems to be something I've done over the years, at least part of the time. Okay, so I didn't mean to pull on that. I don't know what happened. That's the same one. So let's see if I can shrink that down a little bit and go to the next topic, approximating the binomial distribution is where we want to go. So that's the best use of this. There are others, but this is the best one. And we have the mean value and standard deviation of a binomial random variable are mu and p. It's equal to NP. Very easy. And then they're actually using Q. Congratulations. I feel like cheering. NPQ, just a little bit briefer than dragging that binomial all over the place. And so that's the standard deviation. They even skipped the variance. Congratulations. Wow. I'm being a little bit satirical. Sorry. Okay, so now we can find out what we would have if a binomial distribution has n equals 25 and p equals 60%, 0.6. The mean would be that number, 60% of 25 is 15. That would be the mean that you'd expect. Standard deviation, you put the same numbers in. You could just, if you're doing it by hand, you just put the 15 in and then put your Q in, which of course is 0.4, 1 minus 0.6. Then we get a number that's close to 2.5 almost. And so we have a curve that's been superimposed on the probability histogram. And the curve is the exact binomial distribution. That's in blue, the blue blocks. And we're going to try to approximate it with a normal distribution and see how it goes. So we'll look at the probability x equals 10. Now that could be done from the binomial by looking at the capital B, the cumulative distribution function, or we could just get a PDF going and just find the exact answer on your calculator. And or you could subtract the two cumulatives, the 10 minus the 9. So everything up to 10 minus everything up to 9 gives you exactly 10, which is 0.021 to 3 decimal places. Now, if you're looking at the normal curve and approximate that, the z's get transformed into 2.25. The details are not presented. And up to minus 1.84, which is awfully close. In fact, for all we know, it's exactly the same because this is 4 decimals, and that, for some reason, is only 3. I'd rather just keep it at 4 myself, or at least be consistent. So you can see that it's doing a pretty good job. And yeah, it's just like creating As I say, Riemann sums, the little blocks underneath the curve. And you should be familiar with that. It seems like that's one of the first topics. That's what I used to teach. One of the first topics in the calculus we used to do. Anyway, more generally, as long as the binomial histogram is not too skewed, binomial probabilities can be well approximated by normal curve areas. So if P is 0.5 or close to 0.5, then it is not skewed very much. But if it gets too far over, like above 0.7, 0.75, then you can start to see the skewness, the tilt to one side or the other. And so then normal curve wouldn't work quite as well. You get out to 0.9 or 0.1, man, not very good. So they do have a certain way to get around that. You talk about NP being at least 10 and NQ being at least 10. And if that's the case, that seems to settle the issue for the vast majority of cases, and then it's close enough. Okay, so proposition, they go through the mean, NP, sigma, NBQ, square rooted, Q is a possible value of X. And so we just go ahead and make the continuity correction. And they've expanded this out. This is tough to read. Maybe I can blow it up. This is the Z calculation. They just put the continuity correction in there by adding a 0.5. And they put in the mu, they put in the sigma. So there you go. They've already plugged it into the formula. And if they're both greater than or equal to 10, you're okay. But if one of them doesn't make it, then you have to toss it. You'll never get, it's hard to imagine both of them being less than 10. I've never seen one of those. But sometimes one of them be a 9. Or some books just say 5. And, you know, that would be enough too. A little bit looser. This is a little stricter book, I suppose. So, yeah, direct proof of the approximation's validity is quite difficult. Yeah, Okay, we don't need to talk about that. We talk about plenty already in this class, so I'm fine with that. Here's another example. 25% of students at a large public university receive financial aid. X is the number of students in a random sample of size 50 who got the aid. And so P is 0.25. Mu with B is you multiply N times P, a fourth. 0.25 is a fourth, times 50, 12.25. And of course the calculation works out to be 3.06 for sigma. You can do that yourself. But NP, which was the mean, we've already done that one, and it's greater than 10. Good news. And NQ, well, I would just do the larger one. And if it's, I'd do the smaller one. If the smaller one is greater than 10, unless P and Q are equal, of course, P being the smaller one, then that guarantees that Q will be larger and NQ will have to be larger. So if the smaller one got over the line, of course the bigger one will. An approximation can safely be applied, and so they go ahead and do that, and they get your, 10.5 minus the 12.5, which was the mean. They divide by the standard deviation, 3.06. And so to be less than or equal to 10, we have to add in the 0.5. That's the block that includes the 10. 9.5 up to 10.5. And notice with discrete values, the equal sign is quite important. So suddenly we shift gears and say, oh yeah, that equal sign matters now. Before it didn't. So here, we're going to go between 5 and 15 inclusive. That's really from 4.5, the numbers that round into the 5, stopping at just shy of 15.5. We'll just call it 15.5. And that will be how we get it. In fact, they've already done that adjustment too. And if you need to do a sketch, please do so. But what they do is they took the larger number first, including the continuity correction to get that rectangle in there. And they subtracted away the 5 with every number that rounded into the 5, which was 4.5. Of course, the mean and standard deviation are exactly the same as before. And the phi just means that's the cumulative value at that point. This is a table-oriented book, which I'm certainly used to teaching tables, but I realize the reality of the world today, and most people, I believe, unless you just haven't forked over the money, can use a calculator, and that's the way I understand it. Calculators are okay, and other software is not because of issues involved. A standalone calculator is perfectly fine, but once you're on a laptop doing all of this, then you've got access to New York and whoever else, and that's called cheating. So we do not encourage that, but we tell you not to do it on a test. So please don't do it on a test. Calculators should give you all the things you would ever need. And I hope that you have access at least to some sort of calculator, even if you don't use it a lot. Well, anyway, when the objective of our investigation is make an inference about a population proportion P, interest will focus on the sample proportion of successes, X over N, rather than X itself. So that's the P hat. And really just X multiplied by 1 over N. And that's approximately normal distribution with mu equals the P and standard deviation equals, as it turns out, the square root of PQ over N. because we have to divide by the n, and it turns out to work out that way. And same minimums, and it's the basis for several inferential procedures to be used in later chapters. That's another reason to talk about it. We'll be seeing this again. Okay, so yes, 83% was the answer to the last one, and around 26% was the answer to the first one. So that's how we could do it. Now we have several exercises. I do have to watch the time, however. I did work out several of them in 4.3, being an extremely important section. But I do have to watch the time. So what I think I'll do is probably save that for another day, like when we review for the test, or maybe sometime very soon I'll work out some problems in class. But anyway, let's go ahead and skip ahead, and let me zoom back over here and get over to 4.4. Now we have a couple of, I won't say unimportant distributions, but everything compared to the bell curve is not as important. And so the density curve corresponding to any normal distribution is bell-shaped and symmetric, but there are many practical situations where the variable of interest to an investigator might have a skewed distribution. And one of them is called the gamma family. We look at the special case of that, the exponential distribution, and then generalize to the gamma distribution. So there you are. Let's check that out and see about going through this. And I'm not going to spend as much time on this. I do want to hit the examples. And this is what your notes are for, because we don't expect you to memorize these distributions. I had to, but of course I was a stats major, so that's different. And if you think you'd be using this on a regular basis, then by all means, memorize them. But for our purposes, a note sheet is perfectly okay. And I guess I don't need to look at your note sheet, but the note sheet could include worked out examples and all, but it is a low situation. Now it turns out I'm going to have to, I didn't know my computer was out of power, so let me, hold on a second, let me plug it in. I'll be right back. Okay, intermission's over. Sorry. And I can't really pause this right now, but I do have it plugged in, so we will have more time to spend zipping through this last section here. And so exponential, the family of exponential distributions is used widely, and this is the formula itself. Lambda times e to the negative lambda x for any non-negative x, and it's not equal to anything otherwise. And we're not going to worry about that. You can find the mu by attaching the x, just like we did before. E of x, just put the x in front of the main f of x and integrate. And we can use the shortcut formula for the variance and then square root if necessary. As it turns out, though, mu is equal to 1 over lambda, and sigma is also equal to 1 over lambda. Notice I took the square root of both sides. And the variance, of course, if you ever needed that, would be 1 over lambda squared. So yeah, both the mean and the standard deviation are the same. That's unusual, to say the least. And we have a few curves that go with that, such as lambda equaling 1 and lambda equaling 2 jumps up like that, lambda equal 0.5 like that. But here's the 1. Looks almost like 1 over x, but not quite. And it's, well, easily integrated. I took a few moments and integrated it. Yes, it does work. You have to, let u equal negative lambda x and just integrate the exponential function. It's not that big a deal. But we're not going to really depend on having much integration in this class, except for very basic. Perhaps that we'll see. We'll see how it turns out. But let's focus on the examples and see if we can use these distributions. So this article suggests the exponential distribution with mean value of 6 as a model for the distribution of stress range in a certain bridge connection. And let's assume this is in fact the true model, and so the expected value of x is 1 over lambda of 6. That means lambda itself is 1/6, which of course is that very familiar to me decimal, because that's like, expected value of getting like a 2 on a roll of a die, 1 chance out of 6. Okay, so now we have to find probability at the stress range is at most 10, so 10 is the maximum. In other words, x is less than or equal to 10. And so we can then use the CDF, the cumulative distribution function, and plug in the lambda. There it is, 1/6, and minus, and then that times 10 for the x, and plug that in. It's a continuous distribution, so perhaps the less than or equal to is not necessary. The book just blankets it every time with a less than or equal to. Anyway, you get 1 minus that number to be 0.811, 81% of the time, for it to max out at 10 when the mean is 6. That doesn't look very unusual. But to be between 5 and 10, we can then just take a look at the various ways of going. And we just did the 10, so there it is. That's the cumulative value of 0.811. And then we subtract away the calculation at 5, which of course basically cuts this exponent in half. So instead of 1.6, it's 0.8, etc. And then one could calculate that out. The ones actually cancel here. 1 minus 1 is 0. So it's really just this number, then plus that number with the double negative. You get about 25%. And this is frequently used as a model for the distribution of times between the occurrence of successive events, such as customers arriving at a service facility or calls coming into a switchboard. So this is times between. So the Poisson is just a little bit different. And so exponential talks about the amount of time between events. And Poisson distribution, parameter of alpha t, is the number of events occurring in 1 unit at a time. So a little bit different. That counts the number of events occurring in a certain amount of time. Say a minute, say an hour, or a day, whatever it might be. But now the exponential distribution, closely aligned with it, would be the times between successive events to see what that probability would be. And they said it was 6 over here. Okay, anyway, don't need to go too much into the technical details here, but they have gone through and shown a few steps here. And with the alpha t and the 0, the zeros tend to just sort of remove themselves, and then we're back to where we would be before. Okay, this example though, there's calls to a rape crisis center in a certain county occur according to a Poisson process with half a call per day. In other words, a call every other day. But the number of days x between successive calls, which is exponential, would be having a parameter value of 0.5, but then we're interested in more than 2 days that elapse between calls. So, it's already not going to happen all the time, but what about more than 2 days? Well, let's find out. If we have that happening, we'd look at probability of x less than or equal to 2, and that would be, of course, 1 minus, well, it's actually, we use the CDF, and we are actually asked for greater than 2. So to start off, we have 1 minus the CDF, and that would be something we can calculate. And then using the notation which they're using, f of 2 along with 0.5, in other words, the 2 is being used, and the 0.5 is the rate of alpha, so that's really x comma alpha. And so we get the 0.368, and the 1's actually canceled out. 1 minus 1 is gone, and then the minus on this became a plus. They didn't show that step, and so we do get a positive number, which is nice. You can't have negative probabilities. And the expected time, you may have noticed, is 2 days. So you might think that this would be the other 50%, but not really. This is not a normal distribution. You might think if that's the mean is 2 days and we're looking for greater than 2, my first guess is, oh, it's 50-50 because that's the dividing line, but it doesn't really work out that way. It's more like 37%. And this is a memory-less probability, which is interesting because it does not matter what happened before. This has to do with conditional probability, and partial reason for the popularity of this application is the fact that we do not care what happened earlier. It just does not matter. No wear and tear. So it's associated with the parameter lambda. And putting the component into service, we leave for a period of t sub 0 hours and return to find the component still working. Then what's the probability it lasts an additional t hours? It turns out it's exactly what it was earlier. So they go through the conditional argument, and I don't need to spend a great deal of time on this, but it turns out that as I worked through this earlier, we do get some redundancy here. And turns out that if we're going to look at the definition of conditional probability, where, of course, this x being greater than t0 goes in the denominator, and then we have to look at both x being greater than t plus t0 and x being greater than t0. But the thing is, this cancels out because we've already gotten past that. We've gotten t plus t0. Who cares what happened to t0? So the event x greater than t0 in the numerator is redundant. So we just go ahead and look at this one only and scrub the other. This has happened several times in statistics. So they go through all the calculations, and I'm not going to do that, although I worked out them in my book, but I'm not able to write on the screen right now. Not that I would want to anyway, but it does really work out to be e to the minus lambda t. And that's what we had earlier. So, hey, the conditional probability is identical to the original probability, x greater than or equal to t, when the component lasted t hours. So the distribution of additional lifetime is exactly the same as the original distribution of lifetime, which is an advantage in some cases. It shows no effect of wear, but if there is an effect of wear, this is the wrong distribution to use. So it's the distribution of remaining lifetime is independent of current age. So it can be justified to be at least used approximately in many applied problems. In other situations, components actually deteriorate with age. Imagine that. Or occasionally improve with age. Wow. At least up to a certain point. So anyway, you could go to the gamma distribution and a couple of others that we may have a chance to look at briefly. So let's go to the next page. Let's see if I can zoom back and find it. There we go. And so the generalization of the exponential function, basically the last topic of the day, is the gamma distribution. We will give a passing nod to one other distribution, but that's about all we'll do with it. Don't want to go 2 hours on this lecture. So to define the family of gamma distributions, we first need to introduce a function. It plays an important role in many branches of math, and it's called the gamma function. And that is a capital G in Greek. That's the gamma function. Looks like an upside down L, sort of. So here's the distribution. And they have a few characteristics, by the way. And for any alpha greater than 1, gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1, which starts to generate factorials. For any positive integer n, gamma of n is the same as n minus 1 factorial. Wow, okay. It has to be an integer, though. We can't allow other values, and it turns out a non-integer happens to be the square root of pi. I'm not sure when we're going to use that, but that's about 1.77, by the way. And so there you are. Okay, so as we look at the gamma distribution, they have the function here, which is right here. It's tough to see. I'm trying to expand it. There it is. The same thing we just looked at. X has to be non-negative, though, or it doesn't exist. And this implies, well, I'll go through a little bit more algebra. And yes, you could then get 1 out of this if you go ahead and integrate that out. And yes, that satisfies the property of a PDF. It has to have a sum of 1, or we can't use it in statistics. Calculus, you can do any number, any positive number, but here we have to have 1. So, all right, so that was the gamma function. Now we talk about the gamma distribution. Very similar, but not quite the same because it's more complicated. So, do I really want to use this one? Maybe not. Maybe exponential is good enough. But let's at least go through it and see how it goes. We've got alpha and beta both positive. Standard gamma function would have beta equals 1. Beta is another variable that could be put in to give it more breadth, I suppose. And so we have the illustrations. Let's start with this one. This is what I'm most interested in. Beta is equal to 1 here, and it's called the standard gamma density curves. And alpha equals 1 is this one here. The alpha equals 0.6 comes in closer to the origin, 0, 0. Alpha of 5 spreads out almost like a bell curve. And here alpha 2 is like a skewed curve. And then we have other combinations that you may feel free to look at anytime you want. And alpha is referred to as a shape parameter. Changing its value alters the basic shape of the density curve. Okay, so the mean and variance of the random variable x is as follows. E of x is equal to alpha times beta. Variance of x is alpha beta squared, and standard deviation will be beta times the square root of alpha. So once again, a lot of similarities. And when x is a standard gamma RV, then beta is 1, and you would have mu equals just alpha, and variance would equal just alpha again. So we've seen that one already, as it turns out. And now we have this formula, which is rather similar to what we just talked about. It's very much like 4.7, which was back here. 4.7, well, that's on the prior page. Well, anyway, all they did was they replace the x with a y because we're integrating dy ranging from 0 to an x value. So y is kind of a transformation variable, I guess you could say. And so divide by all that. So it's very similar. The math is becoming stuff that we're not going to be using at all, I don't believe. In fact, we even have tables for this, believe it or not. And okay, so as always, when we're going from x equals a to x being between a and b, we can take the CDF of b minus the CDF of a. They do have a table that goes with this, and I guess I could take a look at it. I'm not certain you will have a gamma function on your calculator. So just in case I went this direction, here is that table right here. And I'm going to have to expand this because it's really small. They do mention it is a very small table. And that's okay. We don't want to look at pages and pages of these numbers. So I'll get back to this in just a second. Let's go back to where we are. And this time they're interested in x being between 3 and 5 with alpha equals 2. So they bring the alpha in every time. And okay, so then we can take a look at alpha being 2 and x being 5. That should be a value of 0.960. Let's check it out. So alpha is 2 and x is equal to 5. So the intersection of those numbers is 0.960, just as I thought. And I believe we were trying to subtract away x equals 3, so there's 0.801. Let's verify that that works. Yes, there it is. We're subtracting away 0.801 for a difference of around 16%. And then, of course, you can do exceeding 4. Table is no big deal. For alpha equals 2, that is, here we have our 4 value for x, 0.908. And this one being greater than 4 and a CDF being less than 4, well, we'd have to subtract the total from 1. And then when we do that, we're down to about 9%, 0.092. I'm not quite sure why it's called the incomplete gamma function, but one could introduce the beta as well, and basically we could just divide by the beta, as it turns out. So let's see. They're saying that in the proposition right here, x could have a gamma distribution with parameters alpha and beta, and then for any x greater than 0, the CDF of x is given by the following, and so they just basically divide out the beta. Okay, fine. And so they demonstrate this here in the final example of the day. We have the survival time x in weeks, and a randomly selected male mouse exposed to 250 rads of gamma radiation has, what else? A gamma distribution. Amazing. How did that happen? Okay, well, alpha is 8 and beta is 15. So if I squeeze this down so we can read the whole thing. And there's the source you could check, and they suggest that actually the data suggests it is pretty close, 8.5, but the beta was a little bit off, but we'll just use what we have. And expected survival time now, E of x, would equal alpha times beta, 120 weeks. That's over 2 years. The variance would equal a times beta squared, 1800, and then we'd square root that to get to about 42 weeks as a standard deviation, which is about a third of the expected value. So the probability the mouse survives between 60 and 120 weeks would be, of course, the CDF going below 120 minus the CDF of those going below 60. So, of course, we'd have to divide out by beta according to their suggestion. And 120 over 15 is an 8, along with the alpha equals 8. Beta is already taken care of, so we were just looking at the 8 column. And specifically, the 120 turns into an 8. And the 60 divided by 15 turns into a 4. So as we look at the 8 column, we'll just be looking at 8 minus 4. And I'll just quickly verify that. So we're looking at the 8 column. And then the 8 on the 8 is 0.547. Of course, there's x equals 8 and alpha equals 8. And then we also mentioned that x would equal 4. So there's the 0.051. So 0.547, 0.051 does seem to hook up correctly. And we could subtract those table-wise. And here's where a table is probably useful unless you have a gamma function. And if you do, great, go ahead and try to use that if you'd like. And the probability that a mouse survives at least 30 weeks, of course, well, anyway, the difference from the prior example is just about 50%, 49.6%. To be greater than 30, well, we'd need to, of course, get the cumulative value. And 30 over 15 is 2, so this is f of 2 comma 8. How about the table there? So 2 comma 8, that's going to be 0.997, very large number. So 2 comma 8, so x equals, alpha equals 2, there we go, 0.997. That's not what I got last time. So let's see, comma alpha. Alpha is the last number. I apologize for that. So alpha is the 8, and we're only looking at the 2. So that's 0.001. So I was pointing at the wrong number. So 2 x comma alpha is 2 comma 8, 2 semicolon 8 rather, according to this book. And yeah, 1 minus 0.001 is practically 100%. Let's just say a couple of words about the chi-square distribution before we let you go. The chi-square distribution, and often they drop the D, not this book. It's important. It's the basis of the number of procedures in statistical inference. Many statistics classes cover chi-square. Amongst only 4 distributions they might learn. The bell curve, another version of the bell curve called the t-distribution. The F distribution is the last one, and chi-square would be like the 3rd distribution in a typical stats class. And the central role played by the chi-square distribution in inference springs from its relationship to the normal distribution. And I went through that problem, and it's a little tough to see it, but there is a relationship there. We'll discuss this distribution in more detail as we come along it later. And no, I don't really have any plans to use this semi-complicated distribution here. There's a formula, and it is possible to use it, but we have calculators, we have tables, etc., etc., etc. Now, this Greek letter here looks like an X. Oh no, that's a CH in Greek, a chi. And chi squared is just the name. As far as I'm aware of, there is no chi distribution, but they do call it chi-square, and I cannot remember the story behind that, but there's a story behind that. So many of the values, I guess, need to be squared, but not really. That isn't really the case. And it has to be, non-negative or it just doesn't exist. They always put that little qualifier there. Okay, so I guess that'll about do it. The normal distribution, since we've gone close to an hour, I'll work on some of the problems later on. But I would suggest that you take a look at 4.3, a lot more important than 4.4. I'll just be honest about it. And by the way, in problem number 58 of 4.3, they're saying there's no nice formula for the standard normal CDF, phi of z. Yeah, they're not lying. Fortunately, we don't have to deal with it. I did, but we don't have to deal with that. Okay, anyway, I would suggest problems 28, 29, 30, 31, and I even worked out 36. And I might come back and look at some of those later. All it really does is ask you to find various easy probabilities. Whether you use a table, whether you use a calculator, it does not matter. I'm fond of asking for sketches. I won't overdo it, but I do like my sketches, so we'll see how that works out. I think it's very important for you to use a sketch. It focuses you, I'll put it that way. Well, anyway, that seems to be it for today, and next time we'll go into a brief tour of 4.5, so more miscellaneous distributions, and work through a few examples of them. I'm not going to be covering 4.6 at all, so that will be skipped. I might say just a couple words about it, but we're not going to really have any responsibility for it, whereas we'll have scant a little bit of use for 4.4, 4.5, but I'll have no use for 4.6. It's just a little too technical. Yeah, I'm not going to go in that direction, but we will also start to talk about in the live lecture 5.1, joint probability distributions and random samples. This is a 2- and 3-dimensional scenario with x and y, and we'll cover at least some of it. This is not where a typical statistics class would go, so I'm going to be treading lightly through chapter 5. Much rather get into chapter 8 and 9. So that's kind of my goal, is to get to there. Very important stuff, and 8 and 9 are very similar to each other too, so that's another hidden advantage. Okay, I think I've talked long enough. Let's see if it's pouring rain right now. And anyway, stay dry, stay safe. We'll talk to you live again on Wednesday, St. Patrick's Day, speaking of Irish music that you might hear in the background. Alrighty then, so we'll see you guys later on. Bye-bye.